Guys, we're going to give this another shot here. I've been trying to get this program to work, and it seems to be working now. Let's hopefully I can write, hey, it's working. So we're going to give this a shot here to make this Unit 7 video. I've skipped over the other slides that we covered in class. The next thing we need to get into are the heavy metals and how they're acting as pollutants. So these heavy metals can come from a variety of different sources in our environment. For humans, however, we focus on where we're going to be exposed to them primarily. With lead, when we look at the lead, it's primarily going to be found in our drinking water pipes and in paint pigments. When we look at the paint pigments, it's usually those imported from other countries, because back in the 1980s, America banned lead pigments rather, in our paints that we use for everything, whether it's house paint or paint on toys, things like that. Most other countries have banned lead paint in house paint, but they still use it on those cheap throwaway type of toys. So you'll hear a lot of recalls and things for children's toys, and a lot of times that's lead in them from the paint that they used on the toys. Kids will put the toy in their mouth, playing with it, and then next thing you know, the paint chips off, they ingest it, and then that lead is now in their body. But what we had in America was a lot of lead pipes in our drinking water system. And it might not be the entire pipe made out of lead, but whenever they had to make, say, a 90-degree turn in order to get to like a new street, today we use an actual metal elbow joint to do that. It kind of puts the pieces of pipe together like this. Back in the early days, though, of plumbing, they didn't have those metal joints. They weren't very good at making those. So instead, what they did to save time was they took two pieces of straight pipe, wrapped them with a lead coupler, and that lead was so malleable, meaning it could bend and manipulate the shape and the size of it. They would then just bend the pipe into place, and that lead joint had direct exposure to the water. As the water flowed through it, it would dissolve lead ions out, and the lead ions then would go into the drinking water. When you ended up drinking your water, then you were ingesting lead. Lead exposure for adults is not as problematic as what it is for kids, because it takes considerably more of it in adults to provide harm to them. In children, they're smaller bodies, so it's going to provide a greater impact to them. It acts on the nervous system. So it's going to cause palsies, which are tremors. It's going to cause problems with those involuntary movements, even things like heart rate and breathing, swallowing, things like that. It could disrupt those. In children, though, it's really problematic because it lowers their cognitive development, meaning their brains don't develop the way they should. They're not going to gain a high enough IQ compared to what they could have without that exposure to lead. And the same thing happens with mercury as well, because mercury is another neurologic disruptor. It's going to affect your central nervous system. With mercury, the main source of mercury for us is from burning coal. We burnt the coal, that released the mercuric oxide that was in the coal, and when the coal got up to a high temperature, that mercuric oxide converted over into liquid elemental mercury. That then went up into the atmosphere in the vapor form. When it condensed along with the rain and the snow, that mercury fell back down to the ground. It then washed into the bodies of water, which eventually carried it out to the ocean. So now when we look at ocean caught fish, we're only supposed to eat those maybe once every month or so, because there's so much mercury in them as it bioaccumulated in the tissues and biomagnified through the food chain. The other heavy metal we worry about is arsenic. This is primarily in our drinking water. We got it in there through industry activities and through mining activities. But again, it affects our groundwater and is trapped within our groundwater. So as we drill our wells into those aquifers, a lot of those aquifers are contaminated with arsenic. That gives us an increased rate of cancer and an increased rate of heart disease, cardiovascular disease. Continuing on with that, another problem we face is acid deposition. And acid deposition, it's unrelated to that heavy metal pollution, sort of. There's a little bit of a link to it. But acid deposition is whenever the acids fall back down to the earth. So we end up with sulfuric, which is H2SO4, and nitric acid, HNO3, that end up collecting in the water droplets, and the water droplets will fall as either rain or snow, bringing it back down to the surface of the earth. As that rain or snow falls, it lowers the pH of the soil then, because as it soaks into the soil, it creates those acidic conditions in the soil. Again, we're talking about a pH anywhere lower than 7. 7 being neutral, less than 7 being acidic, greater than 7 being basic or alkaline. So what happens is it's caused by the release of sulfur dioxide and nitrogen dioxide into the air. That sulfur dioxide got there primarily from burning coal, and the nitrogen dioxide was mainly from like diesel engines. When we burnt the diesel fuel, that produced NOx compounds. Both of the NOx and the SOx go up into the atmosphere. So we could have the NOx. What happens with that is it's going to react with the water vapor that's in the sky, and that's going to form the nitric acid. Sorry. I'm messing up here. Let me erase and move it over here a little bit. So we would have that NOx again from the diesel fuel burning. It's going to react with the water vapor in the sky, and it's going to produce nitric acid, which is HNO3. The SOx from burning coal goes up into the sky. It reacts with the water vapor that's up there, and it forms sulfuric acid, which is H2SO4. Both of these processes, you should know the compounds involved and what are the sources and what are the acids that are created from it. One of the problems we see with acid deposition is those hydrogen ions on these acids. When the acids dissociate or break apart in water, those hydrogen ions become problematic to us. That's what makes it more acidic. The higher the concentration of these hydrogen ions, the more acidic the area becomes. And in addition, clay particles, we learned, in the soil have a negative charge on it. And that negative charge is extremely important because that's where the micronutrients bond to. So the sodium ions, which are positive, calcium, which is positive, magnesium, all of those ions that plants need in lesser amounts, not the macronutrients like nitrates and phosphates, but they also need these metal ions to be present in order for proper development and proper fruit growth. If we have an acidic soil, that acid ion, the H plus ion, will start to bind to those negative sites, blocking how much of those micronutrients can attach to the clay. When it gets really acidic, as the plants use these micronutrients, they're replaced with the hydrogen ions, and now new micronutrients can't get in place of it. So that's going to limit how many plants can grow there and affect how much growth the plants will experience. So acid deposition, again, mainly from our industrial facilities, from coal burning and from diesel fuel burning. And again, this just walks you through that. We just talked about both of these. All right, the other type of acidic problem that we have is with acid mine drainage. And acid mine drainage are going to come from the tailing piles and from the abandoned mine shafts. So the tailings are the leftovers from the mining operations. So anything that was not usable mineral gets piled up, or the extra material that we dug out of the ground that didn't contain the ore gets piled up on the site. So these are called either gangue or tailings. You can use either term for it. What happens is there's a decent amount of iron sulfide in that mine tailings. And when it rains on those or water drains over top of them, as the water falls and it percolates down through those piles, that iron sulfide interacts with the water and splits apart. We get free iron ions and free sulfide ions. And what happens is the iron is going to oxidize. It's going to react with the oxygen that's in the water, and it's going to create FeO. FeO is just basically rust, or it can be Fe2O3. You don't need to know that. Just know that it's going to be iron oxide. For the AP exam, if you would list iron oxide as the compound that gives the orangish color to the water, then you'd be fine with that. The other one is more problematic. The sulfide ions are going to react with the water, and that's going to form sulfuric acid. And this is what's going to lower the pH down of the bodies of water. And again, when we learned about aquatic organisms, and any organism for that matter, they have that optimal range of tolerance where they're going to survive, grow, and reproduce the best. If we go to basic or to acidic, away from that pH, So this might be, say, a 6.5, where the organisms are the happiest at. If we make it too acidic, say we get down here into the 4 range, now the organisms have increased stress and they're no longer able to survive and reproduce along with growing. They're going to put all their energy just towards surviving. Reproduction stops, growth stops, and we stop having new babies being born into the population. Eventually, that population will all die off and they'll become extinct. So we need ways to fix this problem. Usually, one of the telltale signs that there's mine drainage in an area is that the stream or the river will have an orangish coating on all the rocks. Because again, that iron oxide is rust, and this is an orangish color. So if we have that orangish color present, we can pretty much guess that it's also going to have sulfuric acid present, or a low pH to the water. So we need to find a way to raise the pH back up. We wouldn't want to add base to the water, because if we'd add something like sodium hydroxide, we'd have to add it in the perfect amount to get the pH right back to normal. And since this water is usually going to be flowing, we'd have to constantly be adding it into it. So instead, what we turn to is a buffer. And the buffer we turn to is going to be limestone, because limestone is calcium carbonate. The carbonate ions are great at neutralizing acids, but it only neutralizes it in the presence of that acid. It's not going to make the water raise in pH rather if the water is not acidic, because it doesn't have any ions to break down. It needs those hydrogen ions to be present in order to act on them and raise the pH up. So what we would do is we would add limestone to this stream, or we would divert the water through a pool of limestone and have that water flow through that. So what we would have is a very low pH upstream, but coming down through here, it would be more of a pH of 7, or whatever the calcium carbonate would neutralize it to. I'm going to pause the recording here for a second because Suvak's on talking about the announcements. I'll be right back. All right, I know that didn't seem like an interruption to you guys because I paused the recording, but it was a pain in the butt. So again, limestone added to the streams as the water flows through that limestone. Again, the limestone is going to help to neutralize that acidic property of that water. So again, very low pH water flows through the limestone, neutralizes the acid in it, and it raises the pH back up to around 7. Sometimes it's slightly higher and a little bit basic. Sometimes it might be 7.5. But again, it raises it back to that healthy level for the fish. So the next form of water pollution is going to be oil contaminations. And when we have oil spills that occur, it could either be from like a tanker hitting ground and draining or leaking oil into the ocean or into a sea, or it could be from like an actual oil rig out in the middle of the ocean leaking out. So we have 3 different things that we do with them. The first one is that we contain the oil with a boom, they call it. So say that this is the pocket of ocean and this is our oil spill here. This is that slick of oil. So the oil is going to be less dense than the water, so it floats to the surface. As it floats to the surface, we want to keep it contained. So we get basically a bunch of pool noodles. It almost looks like. They're not really pool noodles, but they float on the surface, and we surround that oil with those pool noodles. That way it can't expand out. So I guess I shouldn't call them pool noodles. I should say some sort of floating device. They're the containment booms. That's going to keep that oil from spreading out. And then one of the ways we do the cleanup is we'll actually vacuum the oil off of the surface. We'll vacuum it into another ship, take that to the land, and then clean that up on land and process that oil back out. The other thing we can do after it's contained, we can have airplanes fly over and spray chemicals onto the oil. And what that does is it disperses it. Like if you've ever been washing dishes and you add the Dawn dish soap into the skillet that you're washing and you see all that oil run to the sides, those are the chemical bonds breaking within that oil. It's called a dispersant. And that dispersant causes the oil to basically separate into little wee pieces, making it not act as an oil slick now. It kind of spreads out and it's not as impactful to the aquatic organisms. The other thing they started to do was they genetically engineered bacteria to eat the oil itself. So they'll release bacteria on top of the oil, and as those bacteria consume the oil, now it's being cleaned up and broken down into organic molecules by the bacteria. So those are easy ways that we can contain and clean up the oil spills. And again, you can pause this video or pause the video, read what this says here, and go from that. So I'm going to stop and make a second section on solid waste and garbage that gets into the water. So I'm going to pause this because there's going to be kids coming in here for review, and I will pick back up with the second video for you guys here. Welcome back, everybody. We are going to continue on with our notes here. And when we left off with solid waste as our source of pollution that we were leaving off with. And when we look at it, we call that garbage. So anything that we throw in our trash cans, that's going to be the solid waste. But we also include in there other things as well. We can include into that solid waste as the sludge from our sewage treatment plants. This is called municipal solid waste. Because again, it's a municipal sewage treatment plant. That's a service provided by the municipality or the private company hired by the municipality. You then pay them for that service of cleaning up your sewage. So they're going to dispose of that in the landfill, much like we dispose of our garbage in the landfill. But that garbage doesn't always make it to the landfill. You know, picture the garbage truck rolling down the street, and even though they have those compactors to squeeze it all together, some of that garbage blows out of the back of the truck. Or you've all seen around your yard, you know, a raccoon or something like that knocks the garbage can over. That garbage then disperses, and the wind blows it all around. So that doesn't always make it to the landfill. Some of that garbage is going to end up in our environment. And when that garbage ends up in our environment, that's where it starts to impact the living organisms, because it's either going to be a source of pollution directly in the ecosystem, or it could end up breaking down and releasing toxic chemicals into the environment. So that's especially problematic on the beaches. A lot of people will go to the beach, bring cans and bottles and things like that, or toys and games, and then just leave some of that there, whether by accident or on purpose. You know, people will take the bottle caps off and kind of flick them or pitch them at each other. Now those bottle caps become trapped in the sand. Or a little kid's playing with it, drops it, and forgets to pick it up before he leaves. Same thing with the toys. People building sandcastles are a big problem with that, because the kids will build sandcastles, put their toys inside the sandcastle. Then when the tides come in and knock the sandcastle over, now that garbage goes out into the oceans and collects. For a long period of time as well, we actually had people dumping garbage directly into the ocean on purpose, because they weren't willing to go and spend the money to drop it off at a landfill. Dropping it off a bridge into the ocean was a free source for them. And the thought in those communities that did that was that the oceans had an unlimited capacity to absorb pollution. You know, we could just dump anything we wanted into it. They used to go out with large ships and dump barrels of mercury and barrels of toxic compounds right into the ocean, because we thought the ocean would just be able to absorb it forever since it's so big. We've stopped that in our country once we started passing laws like the Clean Air Act and the Clean Water Act. That really started the environmental movement in the 1970s. Once the reuse, reduce, reuse, recycle kind of kicked in, we stopped doing that practice of dumping things in the oceans. But in a lot of developing countries, economically developing countries, they still do that. And you can see the videos on TikTok and other social media platforms of them just dumping entire truckloads of garbage into the oceans. All right, so natural sediment itself is not a pollutant. However, when that sediment starts to cause problems for the living organisms, that's when it is considered to be a pollutant. But sediment itself isn't necessarily a pollutant that we worry about. However, if we have a construction site next to a river, say they're logging out and practicing commercial logging next to a river, when those trees are all cut down, that open soil can erode at a higher rate. So all that water, whenever we get rain, washes that soil and those particles into the river system, and we have an increased rate of sedimentation. Again, natural everyday sedimentation, that's not a big problem. But when we increase that through anthropogenic causes, that's going to be whenever it does become an issue. And any construction site along the streams and rivers can lead to that. Anytime we're taking out that natural root structure or damaging that riparian zone, the riparian zone is the area right near the shore. If we damage the plants along that riparian zone, now the edges of that river continue to erode the stream banks and continue to expand the size of the river, causing that sediment then to go in there. Now, the problems that we face with it, it becomes brown and cloudy, so the organisms needing that extra clear water for photosynthesis or just to be able to hunt and find their prey aren't able to do so. It also reduces sunlight penetration, so our photosynthetic rate, even if they're able to still practice photosynthesis, our photosynthetic rate goes down, and our productivity then also in turn goes down. And again, productivity is the amount of photosynthetic activity or the energy that's produced in a region. So if our productivity goes down, now we can't support as many organisms and things start to die off. But probably one of the biggest ones are the gills of fish. Fish gills are like our lungs. They're interacting with the water, and they take the oxygen directly out of the water so that they can breathe. If we clog those gills up with sediment, with mud, then those gills get clogged up. They're not as good at gaining oxygen, and they end up suffocating. Very similar to what people that smoke experience with like COPD and emphysema. That tobacco particles, the smoke particles, start to collect in their lungs, the tar and everything like that that's in the tobacco. That then builds up in their lungs, clogging up their lungs, not allowing them to get as much oxygen into their body. And instead of having like a 95 to 100% oxygenation of your blood, you might be down into like the 80 to 85 range. And again, this is just what sedimentation would look like. This would be a healthy ecosystem. We see the riparian zone has lots of plants in it, trees are all around, but natural sedimentation occurs. If that water was like a dark brown color, everybody's used to seeing that in our rivers. Every time it rains in Pittsburgh, they show the rivers mixing and that brown color happening. Then that would be when sedimentation gets to the extreme levels and becomes problematic. All right, another thing that we run into is thermal pollution. And thermal pollution can come from anthropogenic causes like power plants, but it can also be from nature as well. If we cut down the trees in an area, and normally the stream was all shaded because the trees provided that natural shade, so that we had the trees here all along the banks, those trees are going to provide the natural shade, which keeps that water at a lower temperature because now the sunlight's not penetrating in. When the sunlight comes down and tries to shine through, it hits the trees, and that's blocking that sunlight. That water stays shaded, and it stays at a much cooler temperature. Now, if we remove those trees and cut them down, now there's nothing stopping that sunlight from hitting directly into the water. That energy absorbs into the water, and now the temperature climbs considerably in that stream. Even though it's a flowing stream, it's always being exposed to the sunlight. That's causing it to rise. The other way that we can have this happen, we learned that with power plants, most of them are going to have a nearby body of water because we need a lot of water in the system for the steam generation and for the cooling of the power plant. I don't know where my cursor went, but let's see if we get here. All right, so there's back now. So let's say that we have our power plant here, and the discharge pipe from that power plant, from the cooling towers, for instance, are putting that water that was cooling the steam down to recondense it again. Let's say that that is dumping into a river, or it could even be a lake. That warmer water that's dumping out of that pipe goes in and heats up the body of water. Just like in the atmosphere, when we have warm air not being able to hold on to as much moisture, warm water can't hold on to as much dissolved oxygen. So anytime the temperature of the water goes up, our dissolved oxygen levels go way down. And we know that dissolved oxygen levels are what provides for that biologic oxygen demand. If we had a high biologic oxygen demand and we input warm water, now our dissolved oxygen goes down and we can't support that biologic oxygen demand at that point. Organisms start to die off. So not only is it going to take it out of that optimal range of tolerance, it's going to move the temperature too hot and put stress on the organisms, but it also lowers that dissolved oxygen for them. All right, and here's a great image. It's a thermal image. We can see that this is probably a power plant here, and it's dumping that warmer water out into the environment. And we can see that local area right around that is definitely going to be affected by it. The fish are going to have to be adapted to a warmer temperature. The fish, again, face those three choices: adapt to that change, migrate away, or die off. If it's a clam or some organism that can't migrate, they're just going to die off once we start increasing that temperature, because we forget about those stationary objects, but those stationary objects need an optimal range of tolerance as well. Now, last one's not super important, but they do trick people up, especially with this one here. When ships use sonar, and we want to call them ships, not boats, because boats are like recreational vehicles. But the ships that are out in the ocean, those are those larger vessels, and the ships need to use sonar in order to find the objects they're looking for. So if it's a fishing vessel, for instance, that ship is going to use sonar to find where the schools of fish are at. They'll then cast their nets and put their nets in the water right exactly where the fish are at, and be able to catch as many as they can. If it's a military-based ship, they're going to be using sonar to find the bottom features and to potentially find enemy targets in the area. That sonar is going to affect the migration of these fish, because the animals use those same things for communication. Just like bats use echolocation on land, mammals like dolphins, for instance, use those squeaks and chirps to be able to tell where each one's at and to be able to communicate back and forth with one another. Whales are the same thing. So if we have a lot of ships out in the ocean, and it's in the migration route of a whale, for instance, now that whale is going to get confused and it may get turned around. And that's why we see the beaching events where the whales swim up on the beach. And we also have reproduction decrease, because the whales can't find their breeding grounds because of this confusion that they experience. Even if it's not on the oceans, even on land, if we have a very, very loud piece of machinery out in the middle of the forest, for instance, with the increased rate of fracking and drilling for natural gas, if it's a nesting site for birds, the birds don't want to be around that really loud thing, so that's going to end up causing them to leave the area. If that was their only breeding grounds and they're endemic to that area, meaning they're only found there, then they don't have a new breeding site and they end up going extinct as a result. So even though noise pollution is not a major impact, it does affect breeding and communication of them. So that's it as far as the aquatic pollution. Now we're into the air pollution, and the air pollution is the one you're more likely to see on the AP exam. So this is the one you want to pay extra close attention to. And when we talk about the air pollution, we tend to focus on the criteria pollutants. And these are those criteria pollutants. When the Clean Air Act was passed, the EPA set 6 pollutants as the ones that they're going to monitor and find the amounts in the atmosphere and regulate how much is tolerable for companies to release. So what we look at is an acronym called NOSCLP, NOSCLP. And you can think about it, it's atmospheric pollution, so you want to plug your nose so that it doesn't get into your nose. The nitrogen compounds we worry about, there's several different ones. It's not just nitrogen dioxide. We call them the NOx compounds. It's going to be mainly nitrogen dioxide, but we also have nitrous oxide and other ones as well. I don't know why my screen just went blank. There it is. So when we look at the N, it's for NOx. The O, I don't know why it's doing this. Hold on, guys. The O is going to be for the ozone up here. So the NOx is the N. The O is the ozone, and this is tropospheric ozone. And that will make more sense in a couple of slides here. But tropospheric ozone is our bad ozone. So the bad ozone, the way that we can remember the different types of ozone we have, it's bad up high. Sorry, that announcement just threw me for a loop. It's not that it's bad up high. It's good up high, bad nearby. So with the ozone, we have 2 different locations for it, tropospheric and stratospheric. The stratospheric is the good ozone. That's the stuff that keeps the UV rays from giving us sunburns and skin cancer. The bad ozone is the tropospheric ozone. That's the stuff that's nearby. The troposphere, again, is the layer closest to the surface of the Earth. Stratosphere is the second layer. So that's the O. The S part of it are the SOx compounds. And we have to have it as SOx compounds because not only do we have sulfur dioxide, but we also have sulfur trioxide that's released. Sulfur dioxide is more the natural released, and the sulfur trioxide is the secondary pollutant form of that sulfur dioxide. But power plants also release some sulfur trioxide directly. So again, with nitrogen dioxide, we also have nitrous oxide as well. Any oxidized form of that nitrogen is the reason why we call it NOx. Any oxidized form of sulfur is the reason why we call it SOx. The L is for lead, and the P is for particulate matter. And we have two types of particulate matter, 2.5 and 10. And that's just the size of the particles. So particulate matter is like the smoke and dust. Anything that's 2.5 or less microns, micrometers, 10 to the minus 6 meters, is 2.5. Anything that's less than 10 microns or micrometers is PM10. So if it falls as greater, if it falls between 2.5 and 10, we call that particulate matter 10. The one that's more impactful to us is the 2.5. Because in your nose, you have the hairs in your nose and then the cilia also in the lungs that prevent that dust from getting in. But the 2.5 is so small that it bypasses those and goes directly into your lungs. That then absorbs it into your blood and can cause you lung cancers and other problems with the toxins getting absorbed directly into your body. So when we look at these more specifically, the criteria pollutants, again, the SOx compounds. With the SOx compounds, this is going to be released primarily from burning coal. But we also have it coming naturally from volcanoes. Right? The problem why we worry about this is a precursor or a primary pollutant, and sulfuric acid is the secondary pollutant. What happens is that sulfur dioxide goes up in the sky, reacts with oxygen, and forms sulfur trioxide. The sulfur trioxide reacts with water vapor, and it's not a catalytic reaction. I know I'm writing it above here, but that's just to save space. Again, the sulfur dioxide reacts with the oxygen to produce sulfur trioxide. Sulfur trioxide reacts with the water to form sulfuric acid. This is our primary pollutant, the one that's released directly. This is our secondary pollutant, formed as a, secondary is what I should have written. This is our secondary pollutant. It's formed as the primary reacts with other things. Again, really, really problematic as we burnt coal. Now they have scrubbers in the coal-fired power plants to reduce as much of that sulfuric acid as we can. Now, last year and the year before, when we had those massive wildfires out in California, they had huge problems with acid rain right afterwards because those forest fires are burning up the trees, and any of that sulfur contained within the trees that they've absorbed over the years through the micronutrients and all that other stuff were released as that sulfur dioxide into the sky. All right, our next one are the NOx compounds. This is going to be primarily from burning diesel. And it's when we burn diesel fuel incompletely. So it's going to be mainly with diesel, but we also have it with gasoline. But cars have something installed in them called a catalytic converter, and the catalytic converters will remove the NOx compounds before it goes out into the environment. What happens is they put ceramics along with platinum in the catalytic converter that's connected to your exhaust system on your car. And people are actually stealing the catalytic converters right now because of the platinum contained within them. But anyway, those catalytic converters get up to a really, really high temperature. And what that does is the gasoline coming through that's uncombusted in your engine, if you're really slamming on the gas, not all the gasoline burns up, and some of that gasoline throws through the back end out the exhaust pipe. That's why if you've ever seen people that light their exhaust on fire and it shoots flames out, that's that uncombusted gasoline. The catalytic converters are so hot that they will oxidize that gasoline and burn it up. In addition, they take that nitrogen dioxide, or the nitrogen dioxide that's produced from incomplete combustion, and they'll break it down into elemental nitrogen because, again, it further oxidizes it and produces water vapor and nitrogen gas at that point. The reason why we worry about the NOx, again, it's an ozone precursor, and we'll talk about that as well. But it's also going to be attributed to that ozone forms photochemical smog, but it's also going to produce nitric acid in our sky. So when the NO2 goes out into the atmosphere, it reacts with the water vapor, and that forms nitric acid. And that nitric acid follows as acid precipitation. So again, this is a big problem, but the major cities have an even bigger problem with the ozone precursor. And one of the things you're going to see throughout is what effect these have on humans. If they're asking for what effect these criteria pollutants have, always go with respiratory irritant. They're going to irritate your respiratory system, and people with asthma and bronchitis are going to be affected negatively by that. They're going to have a harder time breathing. So that's one of the human health effects you can go with any of these criteria pollutants. All right, the carbon oxides. We worry primarily about carbon monoxide. This is the only one that's a criteria pollutant. All right, carbon dioxide is not a criteria pollutant. The EPA does not regulate how much carbon dioxide businesses can produce. But it's still going to be important to us because that's a greenhouse gas. We don't want it to go over 400 parts per million because that's that tipping point. 420 was like the tipping point, 420 parts per million. We're well over 420 now, so we are going to experience long-term climate change, even if we would stop producing carbon dioxide right now. But again, the greenhouse gas effect of these, the heating effect of them, that's the main worry about carbon dioxide. With carbon monoxide, though, it binds the hemoglobin in our blood, and hemoglobin is what brings the oxygen to our tissues. So the more carbon dioxide we inhale, the less oxygenation our blood can support, and we end up suffocating. It gives a effect that causes you to basically get lightheaded, nauseous, and then you end up passing out and dying from it. Carbon monoxide, the big thing is vehicle emissions. Anytime you have incomplete combustion or low temperature combustion, carbon monoxide is formed. So space heaters in houses that burn kerosene, those are a big source of carbon monoxide. Grills are producing carbon monoxide because that charcoal doesn't always burn really hot. So people will think that they're doing something smart by heating their house with their stove whenever it gets cold if the furnace goes out, but that's actually going to produce carbon monoxide. If the furnace isn't functioning properly, that can produce carbon monoxide. So again, it's one of those pollutants that you can't smell or sense, it just makes you sick. And again, we already talked about particulate matter, so I'm going to skip over that one. With this down here, the two different types of smog, we've almost eliminated sulfurous smog because we do clean up our power plants now and reduce the amount of SOx compounds going out. So the SOx is a much lower amount. The photochemical smog, though, this is the one that we do have problems with, and it's going to be linked to that ozone, the tropospheric ozone. That's why, again, good up high, bad nearby. So when we look at, and again, we can skip over lead. We've already talked about that one when we talked about aquatic pollution. VOCs are another big one. VOC stands for volatile organic compound. These are mainly going to be solvents. They're used to dissolve things into them. So cleaning agents a lot of times use VOC-based solvents. Those solvents dissolve in the cleaning agents. We spray them on the thing that we need to clean. That dissolves the oil into it. Then the solvent evaporates off and leaves behind that solid that we can just wipe up afterwards. So those solvents are used in like paints to make paints dry quicker. They're used in cleaning agents, all of those things. And those VOCs, again, they're going to lead to ozone formation as well, that bad tropospheric ozone. All right, we talked about primary versus secondary already. Primaries released directly out. Secondaries are created from the primary pollutants. So if it's a pollutant that's released directly into the atmosphere, that's our primary. If it's formed after it's been in the atmosphere and through a chemical reaction, then it's a secondary reactant. And you can pause the video here. These are our primaries, and the secondaries form through chemical reactions of those. So the one I want to focus on first is ozone and smog formation. So the NOx compounds go up into the sky. Again, that nitrogen dioxide. It's going to be oxidized by the sun. So the sun is a key part of this. When that NOx gets hit with the sun gives enough energy that it splits the molecule apart. We have nitrogen monoxide and a free oxygen. Oxygen is extremely electronegative, so it wants to bond with anything it can find. It's like fluorine and chlorine and those. Remember how in chemistry you had the 7 diatomic elements? We had chlorine, fluorine, oxygen, iodine, and a bunch of other ones. Those are those really electronegative ions that want to bond in any way possible. So that free oxygen is looking for something to bond to. It bonds to an oxygen atom out in the sky, the O2 atom, and that's what forms our ozone. And again, this is tropospheric ozone. Right? That tropospheric ozone is bad for us because, again, what happens is it reacts with that nitrogen monoxide that was formed up here in this step and creates the photochemical smog. So when the sun goes away, the ozone and the nitrogen monoxide further react, and it forms oxygen gas and the NO2. This is after the sun has gone down. Again, in the presence of sun, we have our ozone formed, but at nighttime, that ozone goes back away. So usually the ozone formation is going to be problematic for us only during the daytime and only on the sunniest days. And when we look at the last part of this, again, that NO that was produced is bad. That's what's going to cause this problem for us. Not only do we have the ozone, which is a respiratory irritant in itself, but that ozone is going to help to form this photochemical smog. Once the ozone is made, we have that nitrogen monoxide reacting with VOCs. That's going to produce the photochemical oxidant needed to change that ozone into the brown smog, that photochemical smog. This is going to cause breathing issues for mainly, again, asthmatics and bronchitis people, all that stuff. It's going to affect your lungs. It basically destroys your lung tissues. So again, the main thing with it, it all starts with those NOx compounds, the NO2. The sunlight shines on it and it breaks it apart into the nitrogen monoxide and the free oxygen. This is going to react with the oxygen gas, and this is going to produce ozone. The NO reacts with the VOCs, the volatile organic compounds, and these produce our oxidants. When these two react, this is what forms our photochemical smog. Now, that photochemical smog, again, only during the daytime do we worry about that because the sunlight is the key to it. At nighttime, when the sun goes away, this ozone breaks back down, the nitrogen monoxide bonds back to the oxygen, and we get the O2 and the NO2 back again. So if we were to look at the production of ozone, it's going to be non-existent during the morning. So like if we had time here, right around sunlight, right around that 7 a.m. time frame, and then noon would be here, we see a small amount of that ozone start to form. It peaks out between noon and 3 because that's when the sun's highest in the sky. And then as it starts to get dark, it goes back down again. If we were to look at the photochemical smog formation, that's going to lag behind a little bit because, again, we need those other compounds to form first. We need the ozone to form, and we need the VOCs to be released. So the photochemical smog would be like this pink line. But again, it's going to go away as well because that photochemical smog, once the sunlight breaks down, it loses its reactant because this starts to decrease. Now, the only situation where that's not going to happen is if there's a thermal inversion. And a thermal inversion usually only happens in valleys. Because what happens is, normally speaking, the sunlight comes, it heats up the bottom of the floor, and that air starts to rise up. But when there's a thermal inversion, we get a reversal of what's expected. Because in normal conditions, we would expect it to be warm air closest to the ground and colder air up towards the top. But in a thermal inversion, what happens is that layer of photochemical smog moves in. and it blocks that sunlight out. So what we end up getting is that warm air will rise up and the colder air settles out. So instead of it being that normal situation where we have warm at the bottom, cold at the top, we get cold, warm, and then cold air again. That cold air prevents that warm air from moving upwards and expanding out into the atmosphere. That's going to block all the pollution that's made in this valley. So if there's cars driving, if there's factories burning, all of that pollutant starts to build up until this inversion breaks. The inversion usually needs some sort of a wind pattern or a storm to blow that inversion layer out. Usually this happens, these thermal inversions happen on very calm nights that have a high rate of sunlight the day before, where there's lots of that photochemical smog that's produced. The wind's not blowing, so that air is able to kind of settle in and keep that warm air up here towards the surface. So again, if we look at it, normally we have warm, cool, and cooler, but in a thermal inversion, we have cool, warm, cool. So that, again, pollution layer starts to collect there. So if we look at this, this was a question from the AP exam. They wanted to know why the city would have a higher likelihood of a thermal inversion happening. And it's because these mountain ranges would prevent the winds from blowing inland. That gives us the ability for that warmer air to settle on top of the colder air. Because again, we could have the winds blowing over top of the I don't know why that just did that. Also, we could have the winds blowing over top of the mountains and never mixing the air with it. So I'm going to stop the recording here because fifth period's about to start, and then I will pick back up here with the rest of the video at the end.